Hello everyone, welcome to seminar again. Today we will have Li Bassi to talk about HYPERKÄHLER writing. Thanks.
Thank you, Tommy. Okay, thanks for the introduction, and thank you for being here, or also for not being here, but seeing this anyway. Okay, this is, I prepared a very light talk, so without not that many details, because as this was my understanding during this seminar, you did something about Beauville-Bogomolov decomposition and Calabi-Yau, right? So you looked much more in the Calabi-Yau world. So I wanted to make you see also something about HYPERKÄHLER, which is the other important block of the Beauville-Bogomolov decomposition. And this talk will be first. We will see the two definitions of HYPERKÄHLER, one which is the actual definition of HYPERKÄHLER, the other is the irreducible homomorphic symplectic manifold, or IHS, and how they are linked. Then we will see some known example of HYPERKÄHLER, something about singular setting, and then if we have time, also generic, I will say what I mean by generic HYPERKÄHLER of a given type. Okay, let's start with HYPERKÄHLER manifolds. And IHS manifolds. Okay, so we start by an MG. Later we will recall some notion that you already know. I don't know that much, but so help me if I say something wrong. MG Riemannian manifold. And from now on, we will always assume it to be compact and connected. I will not say it again, but will always be compact and connected. So, as you might know, but I have these notes which are the truth for me. If you take P and Q in M, then the parallel transport operator goes from TPM in TQ of M is an isometry, right? Okay, in particular, now I am going to redefine briefly the holonomic group. That's why I'm doing this thing. Okay, if you take phi from the loops based at P to the automorphism in the isometry of the tangent space in P of M. This is the holonomy representation that is independent of the point chosen, right? Because of the thing we said. Okay? And we define, I think you defined already during this set of talks, but we briefly, the image of phi, this is the holonomy group. Okay, for everybody, this notation, I think is the same you already used, or not?
No, it's okay.
But it's okay, right? Okay, then we have the definition of. Have you already seen the definition of HYPERKÄHLER?
No,
okay.
No.
So we take MG. This is the definition I never used. So of dimension. For the moment, I will try to be in accord with real people, not with complex people, but maybe I will change something later. Dimension for n is HYPERKÄHLER if the holonomy group is isomorphic to SPN, which compact symplectic group, which I recall you to be write it correct, SP of 2nC in U of n, which is also the unitary, the quaternionic unitary group. Okay, so the definition, the first definition given, the more differential one, is a definition in terms of the holonomy of these varieties. Okay? And just seeing that the group of holonomy has to be a certain group, which is the SPN. I think I was here when you explained this. Okay, better. So let's look at some properties that immediately comes from being hyperkähler, and why do in algebraic geometry use more often the other vision that is irreducible homomorphic symplectic manifolds. Okay, in particular, for this thing, we have that if Mg is hyperkähler, then we have an action. This H, how do you call it? Is the half hyperplane? Is it a name? Half complex hyperplane?
The quaternionic space.
Yes, the quaternionic space.
Okay. I don't just quaternions.
Quaternions, the group of quaternions, okay, the quaternions acts on the tangent space under holonomy. By definition of being hyperkähler. And then there is something called the holonomy principle. Did you do the holonomy principle?
I did.
I wrote something, I don't know almost anything about it, but if you're interested and for you is better, where is the holonomy principle? Holonomy principle, that every tensor at P in M invariant under the holonomy can be extended to be a parallel tensor of
Okay.
That's
We more or less saw it very quickly.
Okay.
She told a bit about that, about
Okay.
characterizing
I know
parallel
almost
tensors.
anything about it. That's the truth that came from above, but this implies, from this you can see, that we have an action on the whole Tm, so without the base point. Okay, that's okay. As parallel endomorphism. Okay. In particular, we can choose every lambda in H. Okay, lambda in H, we can fix the basis of H as ijk, as always, we fix I, j, and k equals ij, right? Yeah, for H. And you can write a lambda as ai plus bj plus ck. Okay, so every lambda here with lambda square equals to -1, that means that it is writing a to the square plus b to the square plus c to the square equals 1. So lambda is in a sphere. Okay. We do just the computation of with the ij and k. Okay. Gives an almost complex structure. Let's say a complex structure. because there is the Salomon theorem, right? Salomon theorem. I wrote also this as a truth from the above. This is the sheets of the truth. All those those almost complex structures are integrable. Well, if you have an action of H on the end, a parallel endomorphism, you have that there is a theorem by Salomon that all those lambda square equals 1 in this way gives an almost complex structure, right? Salomon, I think, or Salomon. Salomon, okay. Okay, so all this is true for the moment. And also, we have that G of UV, if you take two vectors, equals to G of lambda U, lambda V, implying that G is Kähler with respect to lambda. This is the definition of being Kähler. One of the possible definitions of being Kähler, right? If you have a Riemannian manifold, being Kähler means the metric is Kähler if it's true for this is true for the complex structure, right? I saw it yesterday on Wikipedia.
Shouldn't that just mean that the metric is Hermitian?
The dimension
is a Hermitian when it's compatible with the complex structure.
Yes, that's not the part of being closed, the Kähler form. You're just saying it's Hermitian at this point, but you missed the second part of being Kähler, which having the Kähler form which is closed. That's just one of the hypotheses Kähler.
If you know that lambda is integrable, then you need the closedness of the Kähler form to conclude that.
Okay,
that's the Kähler metric.
Yes.
Yeah.
Okay,
You've proved
surely
that
you're
it's
right.
Hermitian.
I read the definition of Wikipedia yesterday. Maybe I didn't see closed because it was closed.
Anyway, we already proved that the Visolonomy group implies Kähler metric.
Oh, okay.
Okay, yeah.
So we can just use that. It's
Okay,
okay that you underlined how this action gives a complex structure,
Okay,
which is
yeah,
okay.
yeah.
But we already know that this Holonomy group is a
Okay,
Kähler Holonomy
thanks.
group.
But it's important to say that G is Kähler.
Yeah, for this metric.
Yeah. For this metric is Kähler. Now I don't see it anyway, but if you already proved it.
No, it's
okay.
containing the fact that we have this special holonomy already.
Okay.
But it's okay to remark that
Thanks.
we have several different complex structures.
We're just saying that's the right action to choose if you want a Kähler metric like that. Yeah, if you define your complex structure like that, you should get, absolutely.
Okay, should be okay. Thanks for the remarks. Okay, you're right. But then we have that we call omega lambda G of lambda blank the correspective Kähler form. Just to underline that we have an all S2 of lambda that we can choose for in order to have a Kähler metric. We have an all S2 of Kähler matrix.
Yeah, I believe that the point for us is that you have proved that it's Hermitian in that point.
Yeah, this
for
is
this other complex structure, which is a new complex structure. But since the holonomy will stay that one, it's also Kähler.
Exactly.
I believe that's the correct argument.
Exactly.
Also with respect to a different complex structure.
Exactly. Okay, so we started from Mg and hyperkähler, and we have an whole family of Kähler manifolds. M lambda omega lambda with lambda and S2. Okay? Properties. First one, if we fix E, the complex structure, then we define sigma as omega j plus E omega k. This is an element in H0 of x omega 2 of x, right? Because we sum two differential forms, two differential forms. Then this is symplectic. What does it mean to be symplectic? Being symplectic means to be nowhere degenerate, okay? Or everywhere non-degenerate, okay? Right. I think that M is simply connected. Plus, these are properties that can be proven. It's actually not that hard to prove, but very long. H0 of x omega 2x, this is a very important property, is generated by this sigma. Okay? Fine. Okay. So we've seen this property of any hyperkähler method, and we can arrive at another definition, which is the one I like more. That X compact, compact, I already said that everything is compact. X Kähler manifold. Let's put it compact. Compact Kähler manifold is IHS, irreducible holomorphic symplectic, if two things happen. The first one is that the P1 of X is the identity, so it is simply connected. The second one is that H0 of X omega 2x is generated by a two-form sigma, which is symplectic. Being symplectic is part of the definition, right? It's not immediate. If it exists, sigma symplectic such that generates H0 of x omega 2x. Okay, so this is the definition of irreducible holomorphic symplectic manifold. Normally, at least I give this definition in the complex setting. As I say, you can change setting usually. For example, did you see that here we didn't specify that the dimension has to be, for example, even, but we specified it in the other definition, dimension for n, here and here we didn't specify. This is just because this condition forces us to be even dimension, even complex dimension. So a multiple of 4 of real dimension. And so these are the two words. One is as a definition very differential, very geometric in the terms of polynomial group. Another is also it's very differential because we have this, we have the presence of this form. We ask the presence of this form. Maybe it's a bit more algebraic because we ask the simple connectedness, etc. But they are completely equivalent due to the theorem of Yau, because vice versa. What do we have? We have X IHS manifold. We take alpha in H2 of X R, Kähler class. Our X is Kähler, so we have it. And then Yau theorem. This is a very important theorem. actually, for me, it's not that evident that it's true. I saw the proof. It's very, you construct the things is very beautiful proof, but a priori, I don't see why it should be true. This implies that exists only one Ricci-flat metric G with Kähler class alpha. Okay, so this is just to see that there is an important theorem to see the vice versa. It's not that easy, and then you can prove that G is HYPERKÄHLER on the underlying real manifold. Okay, because also here we have this setting is natural complex setting. This setting is not a natural real setting. So you have the two vision. When you need it when you want to consider it as a real manifold, you use this setting. When you want to use a complex, use it as a complex manifold, you use this setting. Of course, they're the same thing, but you use them to do different stuff. And also, that's why we prefer it in algebraic geometry, because polynomials are beautiful in C, not in R, right? Okay, so we have this. Of course, here you have to fix the Kähler class. IHS manifold with the fixed Kähler class are the same thing as complex irreducible holomorphic manifold with a fixed complex structure. Okay. As we said here, we have an OLS2 of classes to arrive there, so you have to fix something here and fix something there. There you have to fix the complex structure. Okay, so stop with the differential words. Let's go to some algebraic things we do. Also, I think that Beauville-Bogomolov decomposition it's more clear on the differential point of view, the one with the holonomy definition, right? As you said. So it's beautiful to see that both things are true, and actually for the differential word is only Bogomolov the decomposition, not Beauville's, I guess. Yeah, I'm sure. Actually, Beauville says that it's not his, it's Bogomolov's. Okay, the decomposition. Okay. IHS manifolds. First remark that we do, that if X is IHS, then sigma to the n trivializes the canonical, which is wedge to n of x dual, maybe omega 1 of x. That's the canonical. This means that the first Kähler class of X is 0, without invoking the Beauville-Bogomolov and the equivalence to being Ricci-flat and having the first Kähler class, because this is clear. Okay, and I recall here the Beauville-Bogomolov theorem, but you already did it. So you did with the Ricci-flat property, right?
I think it was you named Beauville-Bogomolov at certain point in your talk. Am I right?
I thought you already said.
No, I didn't. But maybe in your talk. Really? Yeah, it was.
I can write
it. Was a formulation about Ricci-flatness.
I can write it very fast.
Okay.
That X is compact Kähler for a manifold with first Chern class equal to 0, that's actually equivalent to asking the Ricci-flatness, then exists a finite étale covering. I don't want to spend word on the étale. This is a schematic word. Just think of finite covering without the étale word. It's more or less the same. Depends on the topology, but the covering. F. Don't put it in YouTube saying that it is the same.
I think we are working on manifolds, so we
Use
should
the
not
same.
mention étale.
Yeah, exactly.
No, yeah, here is the same,
It
but
just covers.
But I don't want the clip of me on YouTube saying étale is just covering. That's what
It would just mean being honest.
Exactly. Okay, yx, where y is just a complex torus times a bunch of Calabi-Yaus times a bunch of HYPERKÄHLER HS manifolds. It's a product of HS and a complex torus. This is the Beauville-Bogomolov. Beware of the finite étale, because there are not all otherwise Enriquez surfaces, etc. Also something that is not here, but definitely worth to study. So this is also a reason why we study HS manifolds, right? You have this nice characterization on the term of the first class, and you study to start to doing them, and also because they are quite easy. Let's see some example of HS manifolds. Examples. Okay? Okay. As I said, the complex dimension has to be even because of the presence of a skew-symmetric form. Otherwise, you cannot have a skew-symmetric form if the complex is odd, obviously. And let's start with the example 0, which are? Not Benedetta, but the other ones. Which is the first example of HS manifold that you can do? Let's go to the lowest dimension possible, which is 2.
4.
Hmm?
4.
Yeah.
Four.
Ah, 4.
K-
Four.
K3 is.
K3.
Non confonderli, Lucas.
Ah, it's from now on all dimensions are complex.
We are stupid, but not that stupid, okay?
Exactly. See, you can see C as R2. I heard something about it. Okay, and well, actually, these are the only one in dimension 2 because you don't have enough space, and this is the definition. Okay, you cannot go way beyond. So K3 surfaces is the nice example. Can you give me an example of a K3 surface? Again, not Benedetta, because
Fermat-quartic.
in which space?
It's CP.
CP.
No, you're right.
Ah, Fermat-quartic, it's true, but it depends on the ambient space, right?
Yeah, I mean, it's.
I can give you a trick if you want.
They
If
are
you give
those
me what?
complete intersections of degrees.
Exactly.
I don't remember which one.
Exactly.
Yes,
But
degree
Fermat-quartic,
Wait.
x0 to the
Yeah.
plus x2 to the 4th plus x3. Also, it has to be a surface. So,
Equals 0.
eh?
Equals 0.
Yeah.
Ah,
The line bar. It has to be a surface, so it was obvious it was P3. Okay?
mhm.
But then you have a formula to compute the degree of the canonical on some sub-varieties, of embedded varieties, which is the junction formula. And so with that, you can also have the formula for complete intersections, because you can iterate also if you have complete intersection. So for example, this we are degree equal 4 in n equals 3. Or we have, for example, a 2-3 intersection in P4. So you do the vanish of f2 equals 0. So let's say of what? x0, x4 homogeneous polynomial, f3, x0, x4 equals 0, so 2-3 intersection. 2 plus 3 equal 5, and the n equal to 4. Oh, it's one more here again. So you can iterate the argument. Well, these are K3 surfaces. Then other example that comes to mind. For example, take S, a K3 surface, and you have to go to generalize this definition. One of the possible ways is to generalize with Calabi-Yau definition and study Calabi-Yau. Another one is with HYPERKÄHLER, as you see. As I said, dimension 2, Calabi-Yau and HYPERKÄHLER coincide, both the definition. Okay? In higher dimension is not true, but what's the first thing that comes to mind to construct an higher dimensional HYPERKÄHLER manifold? You take a K3 surface, and then you consider the length and some subschemes. No, it's not. It's true. This is, but it's not the most natural one. Okay, I was joking. This is the hyperscheme of n points, but let's do like this. You do the product of S with itself n times. Okay. Then this is not that symmetric, so you can consider on this product the action on y of the symmetric group on n elements. And now S is not a wise choice. Another letter for the symmetric group of n elements. Okay, it's okay. Okay. So you consider all the permutation of these vectors. And this is a good choice for our, in order to be an HYPERKÄHLER, right? Because here on S you add the symplectic form. On S. On S times S bunch of times, you just iterate the symplectic form on each factor. And then, but this is not a nice variety, this is not a nice manifold, sorry. So you model it out by this action of symmetric. This is a nice one, right?
Why is symmetry so important?
Why is so important?
Yeah, why do we want to symmetrize?
Because what's the problem here?
Because you are parameterizing unordered angles of points.
Okay,
So you
okay.
don't want to-
Yeah, okay, of course.
Yeah, but from a symplectic point of view, why is it so important? Actually, I thought that this was the question.
No, but it's okay. It's because we want to use to parameterize stuff, factors, so we don't want to care about
Length and subschemes. In
I
theory,
don't-
but
okay.
this is a problem. This is clearly. This is clearly singular.
Singular.
Okay, right? Where is singular? Consider the action of Sn. So whenever you have two elements that are equal here,
Yeah.
this collapse here. Think of a sheet, and you have, for example, 2 with 2k3, S2, and so you want to go from this k3 to this k3, ordering the points, but then when the points are equal is where the sheet
Yeah,
becomes
so
a sheet.
it's clear. It's like
Exactly.
a border.
It's a border. Because you cannot move freely. It's like doing this and this collapses. Whenever two are equal, so when it's S2, you have only one diagonal. So otherwise you have the polydiagonal that we call also diagonal, which is singular. And so we have to resolve this singularity. Do you know a way to resolve some singularities? An universal way to resolve some singularities? You know? Some word? When you work with dynamite, you
blow up.
blow up. Blow up of the diagonal of this object, which is the symmetric product. We call it, now we call it X for the moment. This is the Hilbert scheme on endpoint on a K3 surface. Okay. What's the blow up? Do you know what a blow up is? Do you know? Is
Not sure.
the universal property of blow up is the universal object such that the preimage of the thing you want to blow up, the base, is a Cartier divisor.
That means?
No, okay, that it has a universal property description. Divide, you know what a divisor is?
No.
There are Weil divisor and Cartier divisors. Just see them as hypersurfaces.
Okay.
Hypersurfaces in your manifold.
Yes, it's the formal combination, formal sums.
Yeah, that's the Weil
Okay.
point of view. Then there is
With
the
the
Cartier
Cartier
point of
the Cartier
view,
one.
which is it's a thing. It's more or less the same thing, but with shifts.
Right.
So they're equivalent when everything is smooth,
Mhm.
but when it's not smooth, they're not equivalent.
Okay.
And so you want to take something that is singular and become it Cartier.
Mhm.
And this is a quite nice, it doesn't always work, but it's a nice way to solve singularities. The idea, geometrically, is that if you have a singular point on your surface, for example, you take everything here equal of this, and instead of this point, you put the sphere of directions, which is a P1. For me is a line, for him is a sphere. Okay? So, but you have a sphere of directions, and being singular means that the tangent space in that point is bigger than the dimension of the variety, strictly bigger. And so you make them equal in this way, adding this. Not always will be equal, but this is for surfaces. Then you have to add things that are bigger than a sphere. Okay. And there is a universal way, but this is an hyperkähler. So it's smooth, inherits the symplectic form from S, and inherits everything else from S.
I'm sorry, what's that notation? I can't read.
Hilb
Below blow
N.
up. Hilb.
Hilb N of S, but sometimes it's also S N with square brackets. Hilbert scheme on endpoints.
Okay.
That's the most common one. Actually, when you denote this, you denote this construction. You have in mind this construction. When you say Hilb N of S, you have in mind the Hilbert schemes of points of length N on S. You parameterize this. For example, in S2, element of S2 will be points. Take C here. C will be described formally either by couples of points. This is a length 2 scheme because you have 2 points, or a point and a vector with eta in the tangent space of S at the point P. actually, if you think of vanishing of polynomials, is easier, but I didn't want to see this very algebraic stuff. Okay, but this is quite nice behaved. Obviously, if the dimension is bigger than 2, there are many possibilities of the point. For example, in S3, you will have either 3 distinct points, either a point, the tangent point, and the other point, either a point, a tangent point, and a point in the tangent square. You have greater degenerations. Okay? But for dimension 2 is everything easy. Okay. That's why I always do. This is dimension 4. Sorry. S2 is dimension 4. This is an hyperkähler variety of dimension 2. Yes. Okay. So. Okay, you choose manifold. Then there are other. Then you can deform these varieties, these manifolds. Sorry, we are always in the. Also in differential geometry, there is a difference between varieties of manifold or not?
Yes, but
Okay,
just
no, but
because
also
you use varieties on entire J like usually. That's,
Okay.
okay.
Also here, then I wanted to talk also as varieties, so I have to be careful. These are all manifolds, okay? Because they are all smooth. Then I wanted to say a lot of things, but as we started late, I don't have time, so I will say something just to intrigue you. Okay, so we have an important invariant, which is the second Betti number of x, which is the dimension, for example, of H2 of xz. You can go in homology and see the cohomology and the homology, compute it. These varieties have a very interesting cohomology. And I'm saying like this and then leaving the open world without explaining it. But one of the main reasons why people studying hyperkähler study motifs is because the cohomology of a symplectic an irreducible symplectic manifold or Riemann symplectic manifolds encodes a lot of these manifolds. We have Torelli theorems, we have many stuff. So those are the nice structures, and you can stop at cohomology or go to motifs and study also motifs of this stuff. Then, how many hyperkähler do we know? Is another question. For example, we know a lot of Calabi-Yau manifolds. This is another very important difference. I don't know how many families they are of Calabi-Yaus, but they are a lot. While for hyperkähler manifolds, we have at most 3 families for each dimension, even dimension. What are these? So this is a family of hyperkähler manifolds that exist for each even dimension. There is another construction very much related to this, which is the generalized Kummer varieties that exist for every even dimension. And then there are 2 sporadic examples in dimension 6 and dimension 10. These are all the hyperkähler we know. The last one in dimension 10 was discovered in 1999, I think, so maybe 2000, but at the end of the last century. And we weren't able to discover other for the moment, so maybe 3 are all. Another thing, what does it mean? Family? Family means a family of deformation. So you can do this basically 2 things. I don't want to spend too much time on the deformation theory because it's hard and it's not the objective. But you can either, this is not what is usually done, but you can consider small changes of the topological structure of it, such that it remains hyperkähler. This is a family of deformation, or maintain this, or get the same topology. That's what is done, and change and study small variation of the edge structure. Okay, the edge structure is the structure of the cohomology, this the cohomology ring of this manifolds, and that means family of deformation. In a way, you can deform your variety, and how much can you deform this variety? Well, you can say that to each XHS manifold, we know that H2 of XZ, so the integral, the cohomology, second cohomology with integral coefficient, as a structure of lattice with the Beauville-Bogomolov form, which is a map from H2XZ times H2XZ. So you have two forms, alpha and beta. And maybe let's do like the quadratic form with only alpha. So at alpha alpha, we get Z with we have a pairing. I don't want to, for K3 surface, this pairing is just the intersection of curves. In higher dimension, as we don't have this geometric thing, but we have this important result that for every alpha in H2 of XZ, I'm going to write it with this integral over x of alpha to the n is equal to a constant, which is proper for H hyperkähler manifold. This is due to Fujita constants. This was called Qx of alpha at 2n. Okay? So we have also this thing. I wanted to write at least one integral in my life.
Sorry, what did you write
Gx,
after the integral?
Qx,
G, what?
Gx,
Yes, after that.
Qx, which was this form.
Okay.
23 is just the intersection of alpha at the power of 2n.
Okay.
Okay? And this gives a lattice structure. So you have also this to study. Let's see, of course, so we have that H2 of XZ will be isometric to a certain absolute lattice, and we call this isometry eta. And then to each pair x eta, you can consider the eta of H20 of x. So you can consider the C linear extension of this form, of this isometry. And you consider a map that to each marked with this marking manifold, you associate the image to the C-complex C linear extension of the marking of the symplectic form. This is a way to parameterize our manifold. This is called the period map. I don't want to spend so many words on this, but just we want to look at the dimension of the period domain. The dimension of the period domain, this is not easy to see, but the period domain is omega L. Omega L is just x in the projective side of L tensor C, such that I will write x equal to 0 and x bar equal Okay, this is the period domain. It's not important that you see its explicit definition. This is the linear extension of the form 2x. Okay, but what's the dimension of this space? Parameterizing this. L is a lattice of rank V2 of x, by definition. Here we projectivize, so we have to have one dimension less, as you always do. We impose an open condition, which doesn't get us anything from the point of view of the dimension, and one condition, one closed condition. Okay? So the dimension of omega L for each L will be V2 of x minus 2. Okay? This is important. Why? Because as you can see, you cannot see. If x is of type A3n, Hilbert scheme on n points on a K3 surface, then V2 of x equals to 23. If x is a K3, V2 of x equals 23. Okay? And then the other families we know as other second Betti number. But I want to focus on this for a moment. Because what does it say to us? We were able to parameterize well, I didn't prove, but parameterize well our family of K3n with a dimension, with a space of dimension V2 minus 2. The same for K3. So this space for each n fixed is one bigger than this as a modular space. Take the space of this family, you can deform with one dimension more. What does it mean? This? That the generic element here will not be an Hilbert square on a K3 surface. Because otherwise, an Hilbert scheme of m points on a K3 surface. Otherwise, the spaces would be the same dimension. If we can move in 22 parameters here, and here we have 23, we cannot cover every parameter here with this. Do you agree? So generic elements in the modular space of element of deformation equivalent to K3n are not in the scheme of n points on a K3. Are other things. You can construct them. One of the way, and I will stop with this, no, maybe, let's see, is consider a cubic fourfold. What does it mean? That epsilon is given by the vanishing of a cubic polynomial in x0, x5. So it's simplified. The polynomial is homogeneous, so you consider a cubic fourfold. And then a true remarkable result that if you consider f of x, which is given by the lines, let's see, lines in Y. So you consider the variety of the lines containing this cubic fourfold. This is generic manifold. So there are other ways. One of the ways to see this, if you take F3 to be a generic polynomial, so not a very specific one. Then the finite variety of lines admits, on Y admits an embedding called the Plucker embedding in a P14. And this is a thing that you do with hands. You consider the minors of dimension 2 on the matrix. It's a thing that you take two generic points in P5, you consider vanishing of the minors of the dimension 2 there, you take the matrix of them. There is a very geometric construction of this. And if Y is sufficiently generic, then f of y embeds in this P14, and you can see with this embedding that this is generic. But it's very similar.
Now, what do we mean by generic now? I lost this part.
It's generic because, as I said, a generic element
something
here.
about this extra element dimension that we have. Okay.
Let's say like this, that the finite variety. This is not true, but
what you mean, I'm not sure. What you mean, maybe I got confused, but what you mean is that we have, by deforming K32, we need to have in that moduli space something which is not just a product of two K3, that's what you meant before.
Exactly.
Okay. And so with this construction we can find
This
something,
example.
that's what you mean by generic.
Yeah,
Something
and
that
generic means
it's
also
in the moduli space of K32, but it's not obtained as two copy of a K3 and the construction before. That's the
exactly,
point.
but generic means also that if you take a random one, you get this.
Okay.
Generically, it's statistically, you can these are more, this is a bigger family. Okay, this is
a short pause.
No, but we are finishing.
Okay, okay.
We are finishing in 5 minutes, just to say the concluding words for this thing. This is our way to research this. Then I have automorphic. What wanted to say other than this? We got lost. No, okay, I wanted to say something also about the singular analog, but no, we said enough things already. But just to say that here we consider everything to be smooth. But for example, also in my research, sooner or later you finish the smooth things to check. So in order to have a job, you have to go to singular things, otherwise you don't have a job anymore. Some people say that it's more interesting. I don't think it's more interesting just to continue to be paid. And there are some singular analogs to this construction, is that you allow them to become good singularities, for example, the case of orbifolds. So things that are locally the push of an open of C and with the action of a group. Or something called primitive symplectic varieties or irreducible symplectic varieties that are very much linked to this definition. But I erased the definition of the EHS manifold, but instead of consider the sheaf of holomorphic two forms, which in a singular setting can be dangerous, we consider another sheaf, which is the reflexive form. The singular analog. You basically consider forms only on the smooth part that extends well. Okay? So you consider that, and you carry to other. And then those spaces are richer because we have way more second Betti number that we can reach. What you can think of if you take a K3n and you collapse something big on it, divisor. For example, we take a K3 surface and you collapse a line to a point, the second Betti number, which inputs the topology, goes one less. So you have you cannot collapse everything, but you have ideally this competing number drops a lot. And so you add more and more examples there, and so you're happy. And last thing about the Hodge structure, which I mentioned, why the cubic fourfold is that important, why we did this with construction of the cubic fourfold on another thing. This is because there are many varieties, many manifolds, and the most studies are Fano varieties, which have a canonical that is anti-ample. I don't want to bore with, but there are many varieties that have the Hodge structure very, very similar to the one of a K3 surface. This is one of them, the first of it, and those varieties are used to construct new hyperkähler. This is one of the construction, this is the simplest one. But why we use this variety? Because the Hodge structure, as I said, is the most important thing of them, very similar. Not that, but you are right there. They are encoding this from one point of view. The other point of view is also that they admit the derived category of bounded sheaves on it, dBx, has a nice decomposition in terms of the coefficients of component, etc., etc. So it's a very nice decomposition. It has a decomposition that is very similar to the one on K3. Let's say like this. So they are very linked, and there are these categories, these subcategories that are called K3 categories. It depends on how the self functions work on them. If it works like a shift of the proper found, and there are also the Calabi-Yau categories. And another research path is to study these categories in order to discover how much of the geometry is encoded in this shift. It's actually pretty much. And so one way is to, they're not completely different, but one way is to look at the motifs and the Hodge structure, and another way is to look at the derived categories to see an algorithm. Then, for example, I'm very happy just to work on explicit example where I can write the equations down, that these are the only one. The other ones are very abstract, because you consider, you can construct basically all the hyperkähler conjecture, it's true, are constructed as modular spaces of some stable elements, where stable means something, on the coefficients of component, on some K3 category, let's say like this. So you can construct them also as a modular space of stable sheaves. I use the geometry on that, but you earn a lot of algebraic tools. Like all your algebraic tools, you have them.
Yeah.
That's the digivolve, of course. You can see also in the infinite category word. But
That's why you talk about digivolution. That was
Exactly.
the point of the title.
Yeah. That's the digivolution.
Of course.
Exactly. And that's a very nice research topic also. And that means just what I wanted to finish with this, that we started with a hyperkähler work, very differential, very concrete definition with the holonomic groups that you can see. We went to an equivalent one, more algebraic, more usable for this kind of things with the complex field, etc., etc. And everything here is on the complex field. Then you can also do on finite fields. Okay? Maybe not characteristic different from 2 probably, but as you always do. We are right there. And then from these very concrete things, we have a lot of, the majority of examples we have are example of modular space of stable sheaves on K3 categories on K3. Now, okay, it's very, very abstract thing, and you can use both very algebraic methods, like in the derived categories world, or very differential methods in the first definition. This is why all the geometry world basically likes HYPERKÄHLER. But similar things also with Calabi-Yau. The Ricci-flatness property is a very important property that was needed. Finish.
Are there any questions?
Okay, a quick one, you have time. Okay, quick one. You talk about generalized schema variety, that's the name. Okay, we didn't really see it. So how difficult are they? It's something we skip because the definition
No.
is too
No,
complicated.
because you didn't have time.
Okay,
Same
but
thing.
just a moral definition.
Yeah, you take the same construct. We start with an abelian variety,
Uh-huh.
so you have sum.
Uh-huh.
You take the symmetric product.
Uh-huh.
You do the same thing, but now instead here we do the same thing, so we are
Uh-huh.
here. But then you consider the summation morphism.
The summation
You can
morphism.
sum.
Okay.
Here you have n all
which is an additional symmetry in some sense.
It's,
Okay.
you consider because here if you just resolve it, you lose some job. It's not an hyperkähler. Consider the summation, and then you consider the fiber over 0. You can prove that each fiber over 0. Also with this, we compose. You go back with the fiber over a point. You go here and we do this blow up. And every fiber is a hyperkähler.
Okay.
And you choose the fiber over 0 because 0 is in all the abelian varieties. It's the only thing that you ask. So this is generalized Kummer.
Ah, okay.
It's super easy, super easy. The definition is super easy. Then things on them are, in my opinion, much more difficult. For me, I'm not that strong on them. Also because there is this additional things to take in count and can generate problems. So when you go to singular setting, for example, actually it's a thing I want to do in the next future. We know a lot of Hilbert scheme on endpoints on some singular, mildly singular surface. I didn't find in literature yet anything on generalized Kummer or singular abelian variety. As I think I wanted to. I started to check it like last week.
Okay.
But this additional morphism bears additional difficulties. And for example, the second Betti number is way lower. It's 7. So this is good because you have a smaller lattice, but then the automorphism are different.
Okay.
You gain some, you lose some. While the other two sporadic examples are very abstract. It's very difficult to give them this definition.
Any other questions? Okay, let's start.